Hi everyone, we are back and we are going to do our Pset 2 solution video. So let's go ahead, and this is actually a very good problem to prepare for our exam. It's very similar to a lot of exam problems that you'll probably see in our exam. So let's go ahead and get into it. So we need to, let's get my drawing, got my pen. Identify type of conventional unit cell. So here we know this is simple cubic. This is also simple cubic. And this is FCC. So I like to cross this out, these types of problems. Number of atoms in each cell, 1, 1, 4. We know that from our notes. Number of nearest neighbors, 6, 6, 12. There we go. Nearest neighbor distance is always 2r, 2r in terms of our atomic radii. Lattice parameter. For simple cubic, lattice parameter is also 2r, but for FCC, it's 2r root 2. That's our A. Next nearest neighbor distance, that will be 2r root 2 for both of them. 2r root 2, 2r root 2 for both structures. And the atomic packing factor, so we know this is not close packed, not close packed, and this is going to be 0.74 close packed structure. Are these cells close packed? FCC is. Are any of them primitive unit cells? Yes, simple cubic is primitive unit cell. So there we go. I'm just going to delete this text. So we got that. And again, a lot of those we've kind of seen through the notes, and you can see those in other videos if you want some more information. Determine any crystal, for A, determine the crystallographic directions. All right, so we want to use our format of all, again, so I want to pick, let's go ahead and start with this one. So again, it's finish, which is our arrow, minus our start, which is our starting point. So our finish location is what? It's going to be, finish is going to be where the arrowhead is, finish minus start. So it's a half, 1, 1. So 1/2, 1, 1, minus the start, which is going to be 1/2, 0, 1. So subtract those. So that's going to leave me with, let's see. So it's going to be 0, and then we're going to be left with 1, 0. And that makes sense because it's the same, it's parallel to this direction if we were to draw that. So excellent. So we've got that. Fantastic. What about, let's go ahead now and do this one. So my finish, this is a little bit hard to see. It's pointing at this particular position. So that's going to be my finish. And if you ever have this on exam, you can just kind of explain it or come to me with any questions. So it's going to be right here, 1, 1/2. 1, 1, 1, 1, because that'll be right here, and then half up. 1, 1/2 minus, and then our start is 0, 1, 1. 0, 1, 1. So let's go ahead and subtract that out. So we're left with 1, 0, and then we're left with minus a half. We can't have, again, the minus is in here, so we need to have this be an integer. So we'll multiply everything out by 2, 2, 0, 1. There we go. We got it. What about this one? So again, I'm going to do finish. So finish is going to be 0, 0, half, minus my start, which is going to be 1, 0, 0. So we're left with something that's minus 1, 0, half, which is going to be equal to, multiply everything out, 2, 0, 1. And then finally, let's do this little guy over here. We're going to do our finish, which is 0, 0, 0, minus our start, which is going to be 1/2, 1, 0. So I'm going to go ahead and be a little quicker on this one. So that's going to be 2. Actually, excuse me, not 2. I can't do math. That's why you shouldn't rush. You take your time. These problems are really, again, just take your time when you go through it. -1, because it's going to be minus, and then 2 minus, and then 0. That's it. So there we go. So we've gotten all our directions. Are any directions close packed? Well, this is not necessarily a close packed direction because we're not passing through the atoms, but the direction in general is. So like we've drawn it in such that it's not close packed, but I would say that, again, this is indeed a close packed direction. If we were to put this direction where atoms are, if we were to just translate that slightly, it would indeed be a close packed direction. So only passing through atoms, no empty space. Are any of them crystallographically equivalent directions? There's not pairs. I mean, like these two would be crystallographically equivalent, potentially, and actually this one as well, because you can rearrange them. But anyways, yeah, fantastic. So let's go ahead. I'm going to zoom out here, and let's delete this. Fantastic. All right. For B and C, identify the crystallographic planes. So here we're not passing through our origin, so we can keep that origin there. So we want our intercepts. So our intercept in the X is 1, our intercept in the Y is 1/2, and our intercept in the Z is also 1/2, approximately. And remember, we always know that we take these intercepts and we flip them, reciprocal. So 1, 2, and then minus, or actually equal to 2. So let me get this, draw, please. I wonder if I could pin. I'm going to pin this. Exactly. Let's do this a little bit more efficiently. So this would be my HKL indices. So remember, my HK and L are just the 1 over the intercepts. So good. Here's a little bit trickier because we intercept that origin here. So instead, I'm going to go, and this is going to be my new origin because I have to define my new origin. Now what are my intercepts here? Well, my X-intercept is going to be 1. My Y-intercept is going to be -1. And my Z-intercept is basically infinity. So now I'm going to have 1, 1/2, 0, because I just flipped those. Fantastic. So we've identified the planes, indicate the origin we did. You have to do that. I need to see this. I need to see this as my new, you can call it O prime or whatever, but I need to see that new origin to evaluate your problem. So you must include that. Are any planes close packed? So this is just asking. I'm not asking you to quantitatively calculate that. So we know simple cubic doesn't have close packed planes. FCC does, but it's the 111 family. So no planes are close packed. Indicate the close packed planes for A and C. So A does not have any close packed planes. C does, and it's the family of 111 planes like this. Calculate the planar density quantitatively for the plane in C. So now we're getting into, again, if I ask you quantitatively, then you give me the atomic packing factor. So we have a plane that looks like this here. I'm drawing it because it is indeed rectangular. So this is our A for our lattice parameter, and this is our A root 2 in this plane. Now we see we also have 1, 2, 3, 4, 5, 6 atoms that we're passing through here in our FCC structure. It looks like it has 6, but that's just, again, it's just kind of the way that this is drawn out. It's really not passing through. For example, this is not a basically a central atom here. In fact, I think it's trying to. It's actually a little bit of an error, anyways. Actually, because we're drawing through here, and we're trying to demonstrate that this is the central atom on the back here. So this is just an error there. But anyways, so we have A root 2. All right. So now we're good to go. So we know that this, again, if we have a rectangular or kind of these lattices, it's going to be quarter shared, and this will be half. So we have, so for our planar density, it is going to be number of atoms. So it'll be quarter plus half. So that's going to be 2 times pi r squared over the area of our plane, which is a squared square root of 2. So we know what A is from answering actually the first problem. So now we can go ahead and start to get those done. So I'm just opening up Mathematica. Take some time, stretch, relax a little bit. We'll be good to go. Then we can finish up the rest of our drawing activities and then our really fun. And actually, we're going to go ahead and prepare for the last problem. So we know that R, for example, let's say that our A for simple cubic is equal to 2 times R. We know that our A for BCC is equal to 4 times R divided by square root of 3. We also know that our A of FCC is equal to 2 times square root of 2. So we know those. So now we can say, this is for FCC. Oops, stop. So A, so actually 2 times pi times r squared, and we're going to divide this by A FCC squared times square root of 2. Because again, it's the area of the plane. That's a very important one to remember. So it's not 2 times square root of 2, it's 2r times square root of 2. That'll help. And then I'm going to just do this numerically. 0.55. So that is our planar density. And indeed, it's not 0.9069, so it is not close packed. So we've proven that as well. All right. Draw an FCC cell in D. So boom, 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 boom. And then on each of the faces. So it's always a little bit hard to draw those. So I give myself some leeway there. So that would be my FCC. I'm going to actually just delete this now to give us some room. Now it's asking us to draw this particular direction. So again, so if I'm working backwards now, so 2, 1, minus 1, I need to find something that basically, when I do my finish minus my start, I need something that basically I need to do this is going to be 0 and 1, because this would lead to a minus 1. And then I need this to be like a half 0, and then let's do maybe a half 1. Because that will lead to, once I multiply everything out, that'll give me my correct ratio. So this is my finish. So my finish will be 0, 1 half, 1 half. So again, it's going to look a little bit complicated, but it'll be 1 half. I could draw it like right here. So that's going to be where my little arrow. My start is going to be 1, 1, 0, 1. So now the arrow is going to look like this. So that's going to be the value right there. So good. So we've got that. Now I need to draw the 0, 2, 1 plane as well. So let's go ahead and let's get to that. So if we want to draw this plane and we're working backwards as well, we have to now think about, okay, well, what are my intercepts? So my x-intercept is going to be at infinity, so it's never going to cross my x-axis. My y-intercept is going to be a half, and my z-intercept is going to be a minus 1. So whenever you have a negative, what we're going to have to do, sorry, I'm just moving this over a little bit. When you have a negative and you're trying to draw a plane, I already know I'm going to have to redefine my axes. So what I'm going to do is I am going to say, okay, I need to go down. So I'm going to set this as my new origin. So now this is my new origin. So what is my x-intercept? Never going to cross my x. What about my y-intercept? So my y-intercept is going to be a half. So it's going to cross here. What about my z-intercept? It's going to be a minus 1. So this is going to connect right like so. So now the question becomes, all right, well, how can I kind of draw this plane or connect this plane? Well, it's just going to be something like this. So if I were to redefine my origin like this, at another point, here would be my x here would be my minus 1 here. So the plane is going to look something like this. And there you go. That's it. So we got it. Boom, boom. We're good to go. Calculate the planar density quantitatively of this plane, of my 021 plane. So we're asked to calculate the planar density of the plane quantitatively. Is it close packed? So we already know it's not close packed because in the FCC, it's not one of our planes. So let's go ahead and let's take a peek at this plane. So we're looking at a plane. So we're only at about a half here. So we're gonna have to do a little bit of geometry here. So we know, let's call this plane rectangular. So we're gonna look at here, atoms here, 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 here. It will cross over on the faces on those two sides, but we're not gonna hit here. So we're gonna hit here, 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 and we may hit, let's see. I'm trying to visualize this. Actually, we're going to partially hit these, but we're not going to pass through them entirely. So it's actually going to be partial value. So, you can use, actually, this is a good opportunity. We've actually created a really cool, and I'm going to do Mathematica, a really cool tool. Let's go ahead. So we really can't answer this question fully. Actually, I'm going to download this to desktop. Hopefully it's actually we're going to do the source. From player, we have Mathematica. So this is something that we publish with our students, and again, this is actually very difficult, but very, very cool publication. Yes. We want to do all these things. All right, so we can actually specify, so for example, for a face-centered cubic, and what is the plane? We're looking at O2 minus 1. Let's see. Yeah, O2 minus 1. So we can set this as, we can set these values here. 0. We're going to set this as 2. We're going to set this as minus 1. Now, you can't use this on an exam because, again, we're expecting, I want to see some work. But if you were just curious and you wanted to kind of see how this was going to work, let's see. It's still not. I think we have to wait for it to respond just quickly here. It's reevaluating here. It's a very dense code because, again, it is not a trivial calculation by any means. Here we go. So now we see our, basically it looks like what we have here. So you can see we definitely cut through these planes. See, we're not exactly hitting through the dead center here, so it's only going to be a partial amount. But you can see the planar density calculation up here. And you can always, this is a cool tool too, because we know that 1, 1, and even minus 1. What should be the planar density? Let's check it out. Again, wait patiently. It is a dense code. It's not showing us the correct one there. So let's go ahead. And then let's go back to minus 1. Let's get our correct, because we can see that the intercepts are not. So let it evaluate and work out, and then we'll get our answer here. Oh, it's still stuck on that one. I know this is super exciting, but there you go, 0.9069. See, I'm very proud of that. Anyways, your computer needs to be a little bit robust to run that one. So for our calculations, the way that we've been doing it, I'm not going to go ahead and consider that one. So this is what our plane looks like. We know at this end here that it still has to be of length A, basically. Because, again, we're sitting at that edge here. So now we have to do a little bit of geometry because we have a plane that looks like this, A, or face, right? And then we're looking for something that crosses at, so because we need to find this length. We know that length in this direction A, so we need to find this length here. So we know that this is A, and then we know that it's going to cross here, basically at a half, so that's going to leave with A root 2. So this distance here, x, Pythagorean theorem, so actually we can go ahead and solve. So let's go ahead and pull this in. So it's going to be solve our AFCC squared plus AFCC divided by 2 squared set equal to x squared. And solve for x. Let's do that numerically. So this will be our other value. So if we're counting a fourth, it's going to hit a partial of that. It'll be different from what we saw previously, but our PD will be approximately, again, based on how we've been doing it. So let's see, 1 divided by 4 times pi times r squared. This whole thing divided by our area, divided by the area. Again, this is not the true one, but again, it's just to be consistent, A of SCC times this value here. And there you go. Very, very, very small number. Kind of ridiculously small, but again, it's because this is not really true. It's passing through some other values as well. Actually, should be a half because it's a fourth, so that'll help a bit. But again, not as high as the real one because we're not we're not taking into account that those partial kind of passing through that sphere. But anyway, good. So we need to draw the following directions. So again, we can just go ahead with that same procedure, finish minus start, and we'll. So if I need to make -1, so again, I have a 2 here, so that's going to have to be like a half. So 1/2 minus 1. I'm going to say this is 1, 1, 0, and then I need this to be 1, 0, because that'll make it positive. So I'm just going to start with my start. So 1, 1. So this is my start. My finish will be 1/2, 1, 1. So it'll be like this. Excellent. I'm just going to erase. I'm going to erase in here. Try not to get these. Fantastic. What about the next one? 2, 1, 0. So again, same kind of concept. 1, 0. And then I'm going to do 1/2. Ooh, pen. Where's my pen? Uh-oh. I think we're a little frozen in here. I think we're frozen, so we're going to have to restart this one. Hopefully it's saved. Actually, let's see. Let's see if we can open that up. Get out of your sticky notes for now. Got it. Close your notes. Close. We don't want to see any of that. All right. Let's see if we can reopen these. If not, I'm just going to shut down quickly and then, yeah, let's go ahead and. Sorry, everyone. We are back. Okay, so we need to draw this direction. So again, if I'm going to have the 1, 1, 0, and then I need to have the 1/2, 1, because that will leave me that -1 once we multiply out, and then 1, 1. So 0. So 0, 1. Excuse me. Here we go. 0, 1, 1. That'll be our starting point. And then finish will be 1, 1/2, 1. So look like this. That's our direction. So we can erase there. Hopefully OneNote is happier with what we're doing here. So we got that one. Now we can do -1, -2, 0. So again, now we can have basically, let's do 1/2, 1/2, 1. And then we can have basically 0, 1. And we can have 1, 1. Excellent. So 1, 1, 1. This will be our start. And then finish is 1/2, 0, 1. So we can go here. There we go. That's our directions. Now for the planes. Oops. We have some. Actually, we can just work with this. So for our -1, 0, 2, we know that our x-intercept will be 1, y-intercept will be infinity, and then -1/2. So we're minus, so we know we're going to have to change our origin. So here's our new origin. Here's my intercepts. X at 1, y never, z here at -1/2. So I can go like this. If I were to make this our new intercept over here, we'd get the same thing where we'd have a point here and a point here. So my plane would look like this, coming out of the board there. Fantastic. You can choose different locations, although that is definitely the most convenient for sure. Done. 3, 2, 2. Whenever you have 3, I love these problems because to me they're very straightforward because it's just connect the dots. These ones where there's only 2, when it's rectangular, those can be kind of a little bit difficult for me to visualize. So x is 1/3, y is going to be -1/2, and then our z is going to be 1/2. So I need to set up my new origin differently because the y is minus. So I need to basically set it up on the right side so I can move back to the left. So I'm going to set up my origin right here. This is my new origin. So my x-intercept is 1/3 right here. My y-intercept is -1/2, and my z-intercept is also 1/2. So boom, boom, boom. There we go. That's my plane. That's it. Now, finally, the integral of the first peak is 8. So automatically, this looks like a BCC type, or it looks like a metal. So it doesn't look like a polymer or liquid. And actually, we can kind of see here, the PDF for a semicrystalline will look kind of sharper. So there's going to be lots of peaks here. For an amorphous material, there's going to be wider peaks and a fewer. So then it just flatlines, whereas this kind of keeps kind of going. So broader peaks for the amorphous. For the semicrystalline, it's going to be much sharper. And if it was a gas, it would just be basically like almost flat automatically. Fantastic. So we know this is a metal. If the integral of the first peak is 8, we know that it must be BCC because that's our number of nearest neighbors for our cubic crystal. So we know that this distance, 3.44, is equal to the next nearest neighbor distance of our BCC. This first peak is always 2r. This next one, since we know it's BCC, it's going to be equal to 4r over square root of 3. So now I can use this information to say solve 3.44 equals 4 times r divided by square root of 3. Solve it. So this is my metallic radii. So my metallic radii is 1.48. So I need to look up my periodic. Uh-oh. Do we have this here? If not, we need to go to Canvas. Oops. We need to go to Canvas. Or open up our... We may open up our Google Drive. We may open up our computers here. My laptop. Let's do periodic. Periodic table. Here we go. Never fear, our periodic table is here. So we need a BCC structure, so we're looking for this X. And we can actually, let's see if we can do Control F, 1.48. 0.49. So again, our metallic radii, because it's a metal, will be the first one underneath this. So 0.48. Actually, let's download this here because we'll use it later for sure. Let's open it up. I'm going to look up. Come on. Here we go. Now I'm going to do Control F, and I'm going to look for 1.4. Let's call it 1.49 because that was our, that's pretty much 1.49. So let's look, search, give me something. Did it give me, or is it? Okay, how about 1.48? Here we go. So 1.48. So the previous one was here. All right, yeah, we got it. Doesn't like me. Okay, go to the next one. Where is 1.48? My eyes are betraying me. No. Where is it? And excuse me for the... Alright, 1.48. Usually it highlights it. Here we go. So we can see NB, so 1. But that's not our... The very top one is our covalent radius. So we're looking for metallic radius, and we're looking for that BCC structure. And vanadium, no. I mean, it's pretty close, and this is BCC. So 1.4, 1.47. It'd be nice if we can see something in here. But I don't see anything very clearly right off the bat. There we did miss one. 1.49, tantalum. That's it. So we're working with tantalum. Fantastic. So we've got it. That's the material. And then, again, if we knew, basically, we're given this value. So now that we know R, so that first peak value will just be 2 times this. So the location on our PDF RDF, 2.979. So this would be right here, 2.979. So we want to indicate that as well. Fantastic. So that is our solutions. So we'll see you for the next video. Thanks. Bye.